Hello, good people. Welcome to 4.3 Right Triangle Trigonometry. At this stage in your mathematical career, we should be pretty comfortable with right triangle trigonometry and SOHCAHTOA, where we know that sine is opposite on hypotenuse and cosine is the adjacent on hypotenuse and tangent is the opposite on adjacent. That's where if we have a triangle and we're referencing angle theta here, the opposite side, the hypotenuse, which is actually adjacent to the angle, but because it's the hypotenuse, it gets that name, and this is our adjacent. So it just takes on the ratio, trigonometric functions take on the ratio of side lengths of a right triangle. Hopefully at this stage we also know that cosecant is the reciprocal of sine, and secant is the reciprocal of cosine, and cotangent is the reciprocal of tangent. Okay, I've also talked to you about these, which I refer to as our 2 a.m. wake-up calls. That at 2 a.m. in the morning, I should be able to sneak into your room and say, what's the cosine of t equal to? And you would know immediately it's x on r from a deep sleep. So these, we definitely want to start thinking in terms of these, as well as SOHCAHTOA, opposite hypotenuse and adjacents. They definitely serve their place at times better than these, and there's times where these are better than those. Okay, and if you have not seen the video on unit circle gold, that's in section 4.2. That should convince us that we already know all of these just typical 30, 45, 60 degree reference angles of not only sine, cosine, tangent, but if we know those three, then we also know cosecant, secant, and cotangent. Okay. Let's see here. So here's our reciprocal identities. I'm just going through the things on this page that I believe we probably should already know at this time. We know our reciprocals. You probably recall that tangent is sine on cosine. Cotangent is cosine on sine. That's called a quotient identity because we take the quotient of two trig functions to get another. And to be honest, all of the, not just tangent and cotangent, all of our trigonometric, all 6 trigonometric functions would have a quotient identity. The reason we just talk about these is oftentimes when we're given an equation or an expression that has trig functions in it, we might want to migrate everything into just sines and cosines. So that this allows us to migrate from tangents and cotangents to sines and cosines, whereas cosecants we can get to sines with just 1 on sine and secants 1 on cosine reciprocal identity. Okay, that brings us to Pythagorean identities, and at this stage right now I believe we probably all have been exposed to this one enough that perhaps we have it memorized, but let's talk about all 3 of these. So let's say we have a right triangle in standard position, reference angle theta. This would be the y value or the opposite, the x or the adjacent, the r, the radius we're spinning around on, or of course the hypotenuse. And the Pythagorean relation we know is that x from this is x squared plus y squared is r squared. So if we just call this equation A here, and we take equation A and we divide it by r squared, both sides, we get x squared on r squared plus y squared on r squared equals just 1. And why might we do that? Well, because trigonometric functions are just ratios of side lengths. So we're just going to create ratios here. And x on r is cosine. So this is cosine squared of theta. Y on r, likewise, is sine plus sine squared of theta equals 1. Okay, or perhaps we decide to take equation A and divide both sides by x squared. Then we would get 1 plus y squared on x squared equals r squared on x squared, or 1 plus y on x is tangent. So this would be tangent squared of theta equals, r on x is secant. So this is secant squared of theta. And there we have this Pythagorean identity. Or, of course, our last option would be to take equation A and divide it by y squared. And we would get x squared on y squared plus 1 equals r squared on y squared, or x on y cotangent squared plus 1 equals r on y cosecant. Okay, so here will be my recommendation this time. Let's make absolutely certain we're 100% comfortable with this one. And then let's recognize that tangents and secants live together in a Pythagorean relationship, and cotangents and cosecants live together. And one nice thing about remembering which of these is the biggest, the 1, the tangent squared, or the secant squared, secant and cosecant both have r. This is r on x. This is r on y. Both have r in the numerator, and r is the biggest. So the other elements of the Pythagorean have to add up. They need to add up to become that, because r is always the biggest side. Okay, things that we might not be aware of, this cofunction identity. And here's where oftentimes people will think, well, cotangent and tangent, that's perfect names because they're reciprocals. Why wouldn't sine's reciprocal be called the cosine? Because these are not reciprocals. Well, here's the whole deal with cofunctions. If you take, let's just take a look at our friends, the 30 degree, let's say this is a 30, where this might be square root of 3 on 2, 1/2 and 1 on the unit circle. And let's take a look at our 60 degree angle, where this could be 1/2 if it's on a unit circle, square root of 3 on 2 and 1. These are congruent triangles. They're not just congruent, they're also complementary, 30 degrees, 60 degrees. They're also complementary reference angles down here, where that's a 60, tough to read it. But they're congruent. And so we take a look. All we've done is we've kind of just spun this one around and flipped it over, and we get the same triangle. And that would be the same case as if we had, let's say, a 10 degree angle, reference angle, and then we had with it an 80 degree reference angle with it. Those complementary angles would create these congruent triangles, and what's happened is what was an x value becomes a y value. What was a y value becomes an x value. That's what cofunctions do. Sine, what was y, and cosine becomes x. That would represent this flipping and spinning, and that would represent our complementary angles. The triangles that are just spun around, complements in a right triangle, congruencies. And then we have, let's take a look at tangent. Tangent, the y in cotangent becomes the x becomes the y. We're just spinning and flipping the triangle. It's the same congruent triangle, of just the reference angle switches from being 30 to 60, or from 10 to 80, or anything complementary. And secant is on x, but cosecant changes x into y. So that's why we've got this pi on 2 minus u and u are complementary angles. This is all just one rule. Sine and cosine, tangent and cotangent, secant and cosecant, cosine and sine, cotangent and tangent, cosecant and secant. It's all one rule. And I like to say, if I invented a new trig function and called it star, star of theta would equal costar of pi on 2 minus theta, or 90 degrees minus theta if we're in degree land. So it's only just one rule. And then finally, these even and odd functions. By this stage, we should know that the graph of y equals sine of x looks like this, and it's periodic, so it continues. And looks like this. But the height to the right, if I go the same distance to the left, is the opposite of the height to the left. The height to the right, if I go over this far, is down. If I go over that far over here, is up, but the same height. That makes this an odd function, not odd peculiar, odd mathematically odd, which this says the height to the left is the opposite of the height to the right. Whereas cosine graph and we should know by this time, cosine graph looks like this and continues on. The height to the right is equal to the height to the left. The height to the right, this distance, is equal to the height to the left, the same distance. Now, therefore, the height to the left is equal to the height to the right. It's an even function. And the graph of tangent, by this stage, we should know, looks like this. There's pi on 2, negative pi on 2. Height to the right is the opposite of the height to the left. The height to the left is the opposite of the height to the right. Okay, so if we know the graphs, we can commit these to memory, but if we understand the graph, they're never far away from us. Okay, with that, as I mentioned earlier, 4-3, I just spent more time going through some explanations of things than I will on these problems. I don't think we're going to have too much difficulty on these problems because you've done this in geometry and possibly in algebra 2 as well. Find the exact value of the 6 trig functions of the angle theta shown in the figure. Use the Pythagorean theorem. Sometimes we can just recognize a Pythagorean triple to find the third side of a triangle. So 13 hypotenuse 5, this is 12. Of course, you can get that by saying, for instance, x squared, if we called this x, equals 13 squared minus 5 squared, dot, dot, dot. And now we're just supposed to find the 6 trig functions. So sine opposite on hypotenuse, or if you're looking at this as a reference angle on a rotation, it's the y on r. Opposite on hypotenuse, or y on r, is 5 on 13, making cosecant the reciprocal 13 on 5. Cosine, either x on r or adjacent hypotenuse, 12 on 13, secant 13 on 12, and tangent, if we couldn't see this, is just this on this, and the on 13s cancel. But if we can see it, of course, it's opposite, adjacent, or y on x, making cotangent 12/5. Okay, 16, more of the same. You're going to have a lot of problems in the next 2 sections that look the same. You're basically doing the same thing, building right triangles, maybe doing a little bit of Pythagorean to complete the triangle, and then writing out your 6 trig functions. So here we have, sketch a right triangle corresponding to the trigonometric function of the acute angle theta. So if it's acute, it's going to lie in the first quadrant. Use Pythagorean theorem to determine. Okay, cotangent in our 2 a.m. wake-up calls is x on y. I'd like this to be a fraction, 5 on 1, so this may look something like this, where x is 5 and y is 1. Pythagorean, 25 plus 1, 5 squared plus 1 squared, 25 plus 1, 26, square root of 26. So sine, I'm going to put it over here, unrationalized, of theta, there's theta, is y on r, 1 on square root of 26, or square root of 26 on 26. Let me zoom in just a little bit here. No sense in being that small. We got a whole screen to work with here. And cosecant is the reciprocal, but I'm going to jump back to here. The reciprocal of this is just plain old square root of 26. Cosine x on r, 5 on square root of 26, or 5 square root of 26 on 26. Secant reciprocal, square root of 26 on 5. And tangent, y on x, 1 on 5. Take a look, this on this. The root 26 cancel, the on 26's cancel. We just get left with a 1 on 5, making cotangent 5. So, same as the last problem, it's just we have to do some rationalizing. And cosine equals 3/7. This is 2 a.m. x on r. So I'm not even going to try to draw this to scale. X, maybe it is to scale. Let's see. That's 3 is to 7. I think it would probably be a little bit bigger angle there. Pythagorean, 49 minus 9, 40. Square root of 40 but that's 4 times 10, square root of 4, 2 times square root of 10. 2, I said it, wrote it wrong, times square root of 10. So sine is y on r, well that's fine, 2 square root of 10 on 7. Cosine x on r, 3 on 7. Tangent y on x, or this on that, the on 7's cancel, 2 square root of 10 on 3. Secant's a breeze, 7/3. For cosecant, I'm going to come down here and flip this guy. So cosecant of t is 7 on 2 square root of 10, rationalize times square root of 10 on square root of 10, and I get 7 square root of 10 on 2 times 10, 20. Likewise, cosine 3 on 2 square root of 10, rationalize square root of 10 square root of 10, gives me 3 square root of 10 on 2 times 10, 20. Okay, 20. And finally, some special triangles we'll deal with, 30, 60, 90s, 45, 45s. You should have some experience there. If we were just to pick our favorite values for a 30, 60, 90, we might choose this side to be 1, this side to be 2, twice as long, and this side to be square root of 3. And I'll mention in class, or I've already mentioned in class, depending on when you're viewing this, that people will get these ones mixed up. We don't get the 1 mixed up. The 1's the short side. If we just take a moment and realize the square root of 4 is equal to 2. Square root of 3 is less than 2. 2 has to be the hypotenuse here. There is no reason to make that mistake. 2 is the biggest of the 3 sides. It's the hypotenuse. So I use the short side as a trampoline. In other words, to get from this side to this side, I would come down, I'd find this side, bounce back up, or vice versa. In this case, we're given the 38. To get from square root of 3 to this side, if we're going in this direction, we have to divide by square root of 3. So x is 38 on square root of 3. Or, of course, 38 square root of 3 on 3. To get from this side, the short side, to the long side, we have to multiply by 2. So r is 2 times 38 square root of 3 on 3, or 76 square root of 3 on 3. And sorry about that. 2 times 38 square root of 3 on 3, or 76 square root of 3 on 3. And with that, I believe you're probably in pretty good shape to handle the problems. You may have some questions and answers, but there is your assignment. And don't hesitate to come in if you've got some questions on that. We will have some question and answer time during class. Good luck.